Hey everyone, my name is Marko Vojvodic. I'm a senior engineer on the Cloud Atlas engineering team.
And my name is Josh Matthews, and I'm a senior site reliability engineer on the cloud team.
And today we'll be talking about Let's Encrypt at Scale. So here's a quick agenda. We'll first talk about some key terms like TLS, Let's Encrypt, and ACME. Then we'll talk about our initial architecture that we built out for integrating Let's Encrypt with Atlas. And finally, we'll talk about our second version of the project where we needed to make some changes to the initial architecture to scale this out for MongoDB Atlas. So first, I'll talk about TLS. It stands for Transport Layer Security. It's a cryptographic protocol used to provide security between internet communications, commonly used for encrypting connections between clients and servers. These connections are established using TLS certificates to negotiate keys for encrypting session data. It is the successor to SSL, and it's enabled for all Atlas clusters by default. Let's Encrypt, what is it? It's a free, automated, and open certificate authority run by ISRG. Certificate authorities are authorities that sign TLS certificates and allow you to obtain, revoke, or renew them on demand. We're a sponsor of Let's Encrypt. So what is Let's Encrypt? Let's Encrypt is a free, automated, and open certificate authority run by ISRG. It provides an automated way to obtain TLS certificates that are signed by a root certificate and trusted by most major web browsers. The website is let'sencrypt.org, and we are a sponsor. And finally, let's talk about ACME. So ACME, which stands for Automated Certificate Management Environment, is a protocol for performing certificate authority server interactions in an automated fashion, including certificate requests, domain validation, issuing certificates, renewing certificates, and revoking them. The RFC is 8555 for those who are interested. There's a handy link below. So how does Let's Encrypt actually work? Let's Encrypt implements the ACME protocol, which allows for certificate management agents to automatically obtain certificates without having any manual human intervention. Typically, to obtain a TLS certificate, you would need to sign on to a certificate authority's website, request a certificate, prove to the certificate authority that you own this particular domain that you're requesting a certificate for, and then you'd be able to download that certificate and deploy it to your web servers. On Let's Encrypt, obtaining a certificate is a two-step process. First, your agent program would have to prove to the certificate authority that you control the domain. Following that approval process, the agent will then be able to request, renew, and revoke certificates for that domain on demand. And I'll hand it off to Josh to talk about how to integrate an application with Let's Encrypt.
Great, thanks, Marko. So now I'm going to talk for a bit about how you can go about integrating Let's Encrypt into your application. I'm going to talk about this starting with a small proof of concept application and then scaling up to a large multi-tenant application like what MongoDB Atlas is. So for the sake of this example, I'm going to be talking about a fictional application, which I'll call MongoDB Work From Home, an example that I've chosen for no particular reason. So like I said, let's start talking about a small proof of concept application. So we've got the domain wfh.mongodb.com. It's pointed at a single server somewhere in the cloud that's running a single instance of our application, and we have a few users connecting directly to the server. Pretty typical sort of prototyping stage sort of setup. So we want to use Let's Encrypt to obtain a TLS certificate to secure this connection. So for this sort of setup, probably what you'd end up doing is grabbing certbot, which is the sort of default ACME client that you use with Let's Encrypt, install it on your server and run it. It will reach out to Let's Encrypt, prove that you own the domain that you are currently running it on, issue a certificate, install it, and now you have a secure connection. Now I realize I just skimmed over basically every step of that process, and I promise I will go into detail on each of these things later in this presentation, but for this sort of setup, during this prototyping phase, you want to keep things as simple as possible, and just running certbot is probably perfectly okay. You don't need to think about it more than that. So let's scale up a bit more and talk about a production application. We're now running MongoDB Work From Home as a production app. It's gotten very popular for some reason. So we now have many users and multiple servers running the application in order to handle that load. So how might we go about obtaining Let's Encrypt certificates for all of these servers to secure our users' connections? Well, one way we could do it is just run an Acme client on each of the servers. And this could conceptually work. By default, Let's Encrypt has a rate limit of 50 new certificates per domain per week, where a domain, in this case, our domain would be mongodb.com. And that includes mongodb.com and all variations of subdomains on it. So now let's talk about running an application in a production environment. So you can see here we've scaled up MongoDB Work from Home to a full production application. It's gotten very popular for some reason. So we've got many users and multiple servers running the application in order to handle the load. So how would we go about obtaining Let's Encrypt certificates for all of these servers to secure our users' connections? Well, you could theoretically just do the same thing you're doing with a single server. You could run an Acme client on each of these servers and have them all fetch certificates from Let's Encrypt independently. By default, Let's Encrypt imposes a rate limit of 50 new certificates per domain per week, where domain in this case would be mongodb.com and all variations on mongodb.com and its subdomains. And this limit ignores renewals. So it's perfectly viable that you could maybe scale your infrastructure in such a way that you never have to go over 50 new certificates per week as you bring up new servers and scale your infrastructure. More likely scenario is that you're probably going to want to be running load balancers anyway. So rather than talking directly to your backend servers, users are connecting to a series of load balancers, which then route their connections to into your infrastructure. If you're willing to terminate the TLS connections at the load balancers, then you could instead run Acme clients on the load balancers, have those obtain the certificates, and now the user's connections to your load balancers is secure. And you can then secure the connections within your own infrastructure some other way. For example, you could have a private CA that you use to issue certificates. So now let's talk about scaling somehow even more. So in this scenario, we'll say MongoDB Work from Home has gotten even more popular for some reason. And we want to offer it not just as a single application, but we want to offer a service where we will run a dedicated cluster of MongoDB Work from Home. So someone can go and sign up and have dedicated hardware running their instance of MongoDB Work from Home at a custom subdomain of wfh.mongodb.com. And this is very close to what Atlas is, where we spin up dedicated MongoDB clusters and users can connect to those. So what things do we need to consider in using Let's Encrypt in a setup like this? So the first thing to think about is what host names are we issuing the certificates for? The thing you might be initially tempted to do is issue a wildcard. And this would work with Let's Encrypt and also other existing certificate authorities. You could get a certificate for star.wfh.mongodb.com, and then that would work for all subdomains under wfh.mongodb.com. This works, but it has a couple downsides. Primarily, if something like Heartbleed happens and an attacker is able to gain access to your certificate's private key, there's no separation between the different customers who are running on these subdomains. So someone could get the certificate and then masquerade as customer 1 or customer 2 or whoever at the subdomain. A better thing that you can do with Let's Encrypt is you could issue individual subdomains for your different customers. So when a customer goes and signs up, they get their name.wfh.mongodb.com. So now if, say, customer 1 certificate is stolen, then that certificate only works for customer1.wfh.mongodb.com. It can't be used to perform any sort of man-in-the-middle attack on any of the other customers. And this is a model that only really works with something like Let's Encrypt, where you can very easily and programmatically issue new certificates rather than having to have a human go and click around a web interface somewhere to get them. So the next thing we have to think about in building out this architecture is those Let's Encrypt rate limits I mentioned before. So I said that by default, you get 50 new certificates per domain per week. And if our Let's Encrypt usage is going to be driven by our user interaction, we can't just assume that 50 is going to be enough, and it probably won't be. So fortunately, there is a way to get increased Let's Encrypt rate limits. It's fairly easy. You just go to their site. There's a form you can fill out and say, these are the limits I think I need, and they will get back to you usually within a couple weeks or a little more. And they're very helpful with getting you the limits that you need for your use case. Another thing that you'll need to fill out this form are the Acme account IDs you want the limits increased for. So when you request increased Let's Encrypt rate limits, those increased rate limits are attached to a particular Acme account. So you'll need to go and generate an Acme account and include its ID in your request for raised rate limits. Now, Acme accounts consist of a public-private key pair where the service provider, in this case Let's Encrypt, holds the public key and you hold the private key. So that means you're going to want to keep that private key secure the same you would an API key for something like AWS or other services. This probably means you don't want to distribute that key to every single server that's going to need a TLS certificate, because that's too much exposure in your threat model. What you're going to want to do is have a service somewhere that handles talking to Let's Encrypt on behalf of the servers that are requesting TLS certificates. So with all this in mind, let's look at what that service is going to have to do in order to perform Let's Encrypt operations. This is what I glossed over before at the start, is proving domain ownership in Let's Encrypt. When you request a TLS certificate from Let's Encrypt, it will respond with one or more challenges that you must fulfill to prove that you own the domain. The Acme specification currently defines 3 separate challenges. HTTP 01, you take the challenge, sign it with your private key, and then serve the signed challenge at a particular path via HTTP. And then Let's Encrypt will go fetch the signed challenge and verify that the signature matches. TLS ALPN 01 is another challenge method that is, of course, so easy to say, and also works very similarly to HTTP 01, except instead of serving the signed challenge over HTTP, you're serving it over a special TLS connection. But it's, other than that, functionally identical. The final one, and the one that we're going to focus on, is DNS 01. So in this challenge, you publish the signed challenge to your DNS records, and Let's Encrypt then queries your DNS records to retrieve the signed challenge. And this simplifies a lot of things on your end, because you don't have to figure out how to route the Let's Encrypt requests to whichever server is hosting the signed challenge. You just publish to Route 53 or whatever DNS provider you're using, and then Let's Encrypt figures out how to query it. So we're going to use this for our Let's Encrypt infrastructure. So putting it all together, we're going to have a system that looks like this for issuing Let's Encrypt certificates. I have a few pieces here. Tenant server, in this case, is a server that's going to be running an instance of our application that a customer is going to access and therefore needs TLS certificates. The control service is what I mentioned before. It holds the Let's Encrypt account key, DNS API keys, and whatever other credentials it needs to perform these operations. We have our DNS provider off to the side, which could be whatever DNS provider you have that has an API that you can call, and of course, Let's Encrypt. So to go through the flow of issuing a TLS certificate, we'll see first the server sees that it needs a certificate and makes a request to the control service saying, I need a TLS certificate with such and such host names in it. Your control service should then authorize that request, possibly of something like API keys, and validate that the host names included in this request are host names that this particular server should be allowed to get a TLS certificate for. If all that checks out, it can then make a request to Let's Encrypt saying, order a certificate with such and such host names. Let's Encrypt will respond with a series of challenges for you to complete in order to prove ownership of the domains for which you are requesting a certificate. The control service can then use the private key for your Acme account to sign those challenges and publish them to your DNS provider. After that, Let's Encrypt takes over, queries the challenges from your DNS provider, and if the signatures match, it will issue a cert that the control service can then retrieve and return finally back to the server that initially made the request. Now, there is one thing that I left out of this architecture, which is where does the certificate private key live? So X509 certificates, which are used for TLS, are tied to a public-private key pair. And there are a couple different ways you could go about managing the private keys for these key pairs. So the first thing you could do is you could generate and store the certificate private keys in the control service that is making these requests to Let's Encrypt. So when a server comes up, makes a request and says, I need certificate for such and such domain names, the control service will generate a new key pair. It will generate a certificate signing request that it then sends up to Let's Encrypt. This could be nice because you're able to cache the private key in the control service. And then if you need to, say, replace a server or bring up more servers with the same host name or that use the same certificates in order to scale, rather than needing to request new certificates from Let's Encrypt, you can just serve the cached certificate with private key from the control service and not have to make any external calls. The other thing you could do is you could generate and store the private keys on the machines on which they're going to be used. And in that case, when a server sees that it needs a certificate, it will generate a new public-private key pair and then sign a CSR and send that to the control service, which will then forward that request on to Let's Encrypt. Now, this could be nice because the private keys will never leave the machines on which they're going to be used. They're never sent across the network, so this is fewer moving parts in your threat model. Additionally, if you're storing private keys in the control service, that makes for a single point of failure that a hypothetical attacker could use to retrieve all of the keys for all of your certificates if they were to breach that service. Additionally, storing the keys only on the servers in which they're going to be used means that you need Let's Encrypt to be up in order to get certificates for any particular server. So if you need to boot a new server and it needs a TLS certificate and Let's Encrypt is down, you just won't be able to get a certificate until Let's Encrypt comes back up. They have very little downtime, but they do occasionally have some, so this is something to consider. Now, the only part of the diagram that I showed before that changes depending on these decisions is this part right here. So the initial request from the tenant server to the control service and the response from the control service down to the tenant. If you're storing the keys only on the servers, then the requests from the tenant server will include the CSR, like I mentioned, and then the response from the control service will just be the issued certificate. Whereas if you're storing all the keys in the control service, then the initial request will just be some sort of API call saying I need a cert for these domain names, and then the response back at the end will include the cert plus the private key needed to use that certificate. For what it's worth, we've gone with the second option. We are storing keys only on the machines on which they will be used in Atlas. Great, so now I'm going to hand it back to Marco to talk about some of the minutiae of what we had to do to adapt and scale this architecture to work with MongoDB Atlas.
Thanks, Josh. So yeah, let's talk a bit about what we had to do to scale our Let's Encrypt usage on MongoDB Atlas. As with many major architecture change in software development, we encountered a few issues during development that required us to sort of change the approach and change the implementation that we made in order to securely and robustly deploy this to production. So first, I want to talk about the certificate subject names. In the V1 initial implementation, where we are using a certificate per node, as Josh mentioned, for the certificate subject name was essentially the host name of each node. So here's an example below where we would have essentially one subject name in the certificate, and that's what we would submit in the certificate signing request. Functionally, this worked great with the architecture and the rate limits that Let's Encrypt enforces. However, there's something called certificate transparency logs. So we discovered that Let's Encrypt publishes these logs almost before releasing to production. And certificate transparency is essentially a system for logging and monitoring the issuance of TLS certificates by a certificate authority. So Let's Encrypt actually logs all the certificates that it issues to these certificates transparency logs. And these logs are publicly searchable using a tool like crt.sh. So an example of what you can find by searching for a particular domain on crt.sh is the picture here. So you can see in the section at the bottom the certificate and the details of the certificate. And most importantly, in the subject, you can see the common name that we provided in the certificate. So why is this important to Atlas users or Atlas customers? In the Atlas hostnames, we actually embed various metadata in a programmatic way. This includes things like the cluster name, the project pin, which is a unique identifier for each Atlas project, and other various information related to the cluster topology, such as the replica set type index, replica set index, and replica set member indexes. And these are all nested under the top-level domain, in our case, mongodb.net. So one thing that we noticed is the cluster name is embedded in each hostname. Certain customers may name their clusters after a project name or the company name in order to be able to easily identify them. By including this information in the certificates that we were obtaining from Let's Encrypt, and by noticing that these certificates were publicly searchable using something like crt.sh, we discovered that the sensitive names that customers may have been providing in their clusters would be publicly searchable. And that's not something that we were willing to sort of expose in such a public forum. So we weighed some of our options, and we ended up deciding on revamping the way that we create our host names for Atlas clusters. So you'll notice in this old format that we have cluster name and the project pin. These are all nestled under the same DNS label under the top-level domain. Under the revamp, we actually changed it so that each project had its own subdomain. So all of the sort of cluster-specific metadata for an Atlas cluster, we moved to its own DNS label, and we isolated the project pin, which is unique per Atlas project, into its own DNS label. And essentially what that allowed us to do was to obfuscate cluster-sensitive information by using wildcard certificates. So in the initial implementation, each certificate used the host name of the machine that was requesting the certificate as its subject name. Following that, in the second version, we actually had each machine request a certificate with the project-specific wildcard. So this allows us to still use the architecture where each machine is requesting its own certificate, it's generating its own private-public key pair, and using that to obtain a certificate. But they are all actually using these wildcard domains for the project. But sort of refactoring the code in this way caused us to hit a rate limit that we weren't hitting before. So Let's Encrypt, the default rate limit for duplicate certificates is 5 per week. And according to their documentation, Let's Encrypt defines a duplicate certificate as a request that contains the exact same set of host names. So in the example below, you have www.example.com and example.com. These are all nestled under the same top-level domain. And so essentially anything that was under the same top-level domain that was being requested with the same name was causing issues. So how does this change for us? So previously, we were requesting one certificate or sort of each certificate had its own unique host name. But now we were requesting certificates that were all using the same project level wildcard domain. So for a 3-node replica set, this is fine. Each node requests one certificate, and it has the wildcard domain, and we only hit a rate limit of 3. No problems there. If we want to provision a 5-node replica set, that's also fine, because if each node is requesting one certificate that has the project level wildcard domain, we hit 5, and as long as we don't request any more for that week, we will encounter no rate limiting issues. However, suppose somebody wanted to provision a 7-node replica set, or somebody wanted to create a 2-node sharded cluster where each shard, or two-sharded cluster where each shard had 3 replica set members. We would easily hit that rate limit, and we wouldn't be able to actually provision that cluster on Atlas, and we would essentially deny the service to a customer. So thinking more about that rate limit that was defined earlier, where a duplicate is considered a request with the same set of host names, we came up with an idea to embed or add a unique domain per node that we included in each certificate signing request, and ran it by Let's Encrypt, and they essentially approved the idea, saying that it was a good workaround. So for each certificate, we essentially added these subject alternative names to the certificate, and these included a unique host ID subdomain that allowed us to bypass this rate limit and make each request actually adhere to the certificates per subdomain limit that Josh talked about earlier. So now that we are using these sort of unique domains and we've added to the number of domains that we include in each certificate signing request, we started noticing performance issues where our certificates were taking much longer to be authorized and for us to process all the challenges. That's because we were essentially processing each challenge serially for each domain. We looked through the documentation, we noticed that Let's Encrypt caches successful authorizations. So if you successfully prove a challenge that you own a domain like star.mongodb.net, Let's Encrypt will actually cache that authorization as successful for 30 days from the time of validation. So what that means is any subsequent request will actually not need to prove that it owns a domain if that domain has already been proven successfully. So an example of the application that we used for this in Atlas is, suppose we have 2 certificate signing requests for 2 nodes in 2 different projects. So the certificate signing request 0 includes the star.abcde.mongodb.net domain and the top level mongodb.net domain for backwards compatibility. Certificate signing request 1 is for a different project level subdomain, but also includes the top level star.mongodb.net subdomain for backwards compatibility. So we know that the project level domains actually don't overlap. And so we can submit essentially challenges for those at the same time to Let's Encrypt. But something we noticed is for different CSRs that request the same domain, the challenges that are provided for those domains may not be the same. So if we had 2 certificate signing requests that are both asking for star.mongodb.net to be validated for their certificates, the challenges returned in each certificate signing request might actually have different tokens that we needed to publish to the DNS records to prove that we own those domains. And so if we were to do these in parallel, so let's talk about an example of how this applies to Atlas. Suppose we have 2 certificate signing requests, one for star.abcde.mongodb.net and the top level wildcard domain, and one for star.zyxwv.mongodb.net and the top level mongodb.net wildcard. If we were not using cached authorizations, we would need to prove each subdomain once, or each domain once. And we would have to do these serially in order to ensure that we won't stepping over each other. Now, we know that for domains that don't overlap, we can actually execute those challenges in parallel. But for domains that do overlap, we would need to do those serially. So in this particular case, the service would be able to process the challenges for the project level wildcard domains at the same time. But then we would need to serially process the mongodb.net wildcard domain in order to ensure that we are not overwriting challenges. We noticed that for each CSR that was submitted, if they were submitted for the same domain, the challenge value for the same domain might actually differ between the CSRs. So in early iterations of the project, we noticed that we could be overwriting the values of challenges if we were executing these in parallel. And so we had to start doing these in serial in order to not do that. and make our Acme challenges fail. Now, this causes issues if you scale to hundreds or thousands of nodes that are all requesting the same domain. You will now need to redo a bunch of work that was not necessary. So if we're doing cache authorizations, actually what happens is we can execute the project level wildcard domains in parallel. And we can also execute the top level wildcard domain in parallel for the first certificate signing request, but we can't execute the top level wildcard challenges in parallel across the two certificate signing requests. However, if we validate in the first certificate signing request and prove that we own startup.mongodb.net, when it comes time to validate that we own it in the second certificate signing request, Let's Encrypt will actually return to us that it's already valid and that we've already proven it, and we don't need to do any additional work. So by making our implementation more cognizant of the status of each challenge and checking to make sure that it's already valid before trying to process it, we were able to parallelize our challenge processing to only work on the essentially project level wildcard domains and the unique domains mentioned earlier. And for projects with multiple clusters, this essentially boils down to having to only process the unique host domains for new clusters, and only every 30 days have to reprocess or reprove that we own the project level wildcard domains. Another micro optimization essentially that we made is something called pre-authorization. So Acme protocol defines pre-authorization, but Let's Encrypt does not support it. Pre-authorization is a way to prove that you own a domain before you actually request a certificate. But since Let's Encrypt doesn't actually support the pre-authorization portion of the Acme protocol yet, there is a way to implicitly do it by submitting an Acme order, completing the authorizations in order to cache those valid authorizations, and then explicitly not executing the order to download a certificate. So what this means is when we are spinning up virtual machines while creating or provisioning Atlas clusters, we can start doing the pre-authorization in order to cache the valid authorizations for each domain that the node will request in its certificate signing requests, such that when the machine boots up and the certificate manager on the machine goes to creates a CSR and requests a certificate from the service plane, we will actually be able to immediately submit that to Let's Encrypt. Let's Encrypt will return that all the domains are valid, and we can serve a certificate directly to the machine. By doing this, we were able to minimize the amount of time between booting up a machine and actually being able to use an SSL or TLS certificate on those machines. So great. We implemented all of this and we've scaled out. What's the numbers? So we've issued over 300,000 certificates on Let's Encrypt since we've released this to production. We were able to easily rotate 30,000 and more certificates across Atlas in a day when Let's Encrypt had a CAA rechecking issue back in February, where they actually needed to revoke a small percentage of their certificates issued. And we were able to do this almost essentially with the click of a button. So it was great to be able to do that with minimal human intervention needed. Throughout this project, we realized that security is constantly a moving target, and Let's Encrypt made it extremely easy for us to automate TLS certificate management at a large scale. And this project took about 5 engineers an entire year to complete. So we really want to thank everyone who worked on this project, both from the engineering side, the SRE side, and everyone in between.